Have you ever wondered, what is the maximum amount of solute that can be loaded onto a chromatography column? That's where dynamic binding capacity, or DBC, comes into play. Dynamic binding capacity is a crucial parameter in chromatography, especially when purifying biomolecules such as proteins, antibodies, and nucleic acids. It refers to the maximum amount of solute, or target molecule, that a chromatography column can hold while still achieving acceptable purity and yield. Now let's delve into what exactly DBC is. Dynamic binding capacity is defined as the maximum amount of solute that binds to the chromatography resin under dynamic conditions. These dynamic conditions refer to the flow of the mobile phase through the column during the loading, washing, and elution steps. Several factors can affect DBC. First, there's the resin properties. The type and properties of the chromatography resin greatly influence the DBC. Things like pore size, surface area, ligand density, and ligand chemistry all play important roles. Next are the operating conditions. Parameters such as flow rate, buffer composition, pH, and temperature can all impact DBC. The optimal conditions must strike a balance between high binding capacity and efficient mass transfer kinetics. Third, the characteristics of the sample can influence its binding capacity. The properties of the target molecule, like size, charge, hydrophobicity, and affinity for the stationary phase, all come into play. DBC is typically measured through breakthrough experiments. In these experiments, the solute is loaded onto the column until breakthrough, or when the solute starts eluting from the column, is observed. The amount of solute loaded at breakthrough corresponds to the DBC. Optimizing DBC involves fine-tuning various parameters. This can entail screening different chromatography resins, adjusting operating conditions, optimizing sample loading volume and concentration, and considering the overall purification strategy. However, keep in mind that DBC measured at a small scale may not directly translate to larger-scale chromatography. Factors such as column dimensions, flow dynamics, and packing heterogeneity can affect DBC at larger scales. Therefore, scale-up studies are necessary to ensure consistent performance. Scene script. DBC plays a vital role in process development and optimization in various biopharmaceutical and biotechnology applications. These include protein purification, antibody purification, vaccine production, and gene therapy. It directly impacts process efficiency, productivity, and cost-effectiveness. To wrap it up, dynamic binding capacity is a fundamental parameter in chromatography. It represents the maximum amount of solute that can bind to the chromatography resin under dynamic flow conditions. The optimization of DBC is absolutely essential for efficient and cost-effective purification processes in the biopharmaceutical and biotechnology industries.